Chapter 11. Inferential Statistics. Introduction. Descriptive statistics are but one type of statistic that researchers use to analyze their data. Many times, they also wish to make inferences about a population on the basis of data obtained from a sample. Various inferential statistics techniques allow them to do this. This chapter presents several such techniques and discusses when they are warranted and when they are not warranted in educational research. What are inferential statistics? Inferential statistics refer to certain procedures that allow researchers to make inferences about a population based on data obtained from a sample. The term probability, as used in research, refers to the predicted relative frequency with which a given event will occur. 2. The logic of inferential statistics. A. Sampling error. The term sampling error refers to the variations in sample statistics that occur as a result of repeated sampling from the same population. B. Distribution of sample means. A sampling distribution of means is a frequency distribution resulting from plotting the means of a very large number of samples from the same population. C. Standard error of the mean. The standard error of the mean is the standard deviation of a sampling distribution of means. The standard error of the difference between means is the standard deviation of a sampling distribution of differences between sample means. The sampling distribution of the mean, or any descriptive statistic, is the distribution of the means, or other statistic, obtained, theoretically, from an infinitely large number of samples of the same size. The shape of the sampling distribution in many, but not all, cases is the shape of the normal distribution. The SEM, standard error of the mean, that is, the standard deviation of a sampling distribution of means, can be estimated by dividing the standard deviation of the sample by the square root of the sample size minus 1. The frequency with which a particular sample mean will occur can be estimated by using z-scores based on sample data to indicate its position in the sampling distribution. D. Confidence intervals. A confidence interval is a region extending both above and below a sample statistic, such as a sample mean, within which a population parameter, such as the population mean, may be said to fall with a specified probability of being wrong. E. Confidence intervals and probability. Probability is nothing more than predicted relative occurrence, or relative frequency. F. Comparing more than one sample. Typically, researchers want to compare two or more samples. For example, a researcher might want to determine if there is a difference in attitude between fourth-grade boys and girls in mathematics, whether there is a difference in achievement between students taught by the discussion method as compared to the lecture method, and so forth. G. The standard error of the difference between sample means. Differences between sample means are also likely to be normally distributed. The distribution of differences between sample means also has its own mean and standard deviation. The mean of the sampling distribution of differences between sample means is equal to the difference between the means of the two populations. The standard deviation of this distribution is called the standard error of the difference. 3. Hypothesis testing. A. The null hypothesis. The null hypothesis typically specifies that there is no relationship in the population. The null hypothesis most commonly used specifies there is no relationship in the population. The researcher then proceeds to test the null hypothesis. The same information is needed as before, the knowledge that the sampling distribution is normal and the calculated standard error of the difference, said. A hypothesis test uses 0 as the mean of the sampling distribution instead of using the obtained sample value, e.g., the obtained difference between sample means. Researchers can then determine the probability of obtaining a particular sample value by seeing where such a value falls on the sampling distribution. If the probability is small, the null hypothesis is rejected, thereby providing support for the research hypothesis. The results are said to be statistically significant. B. Hypothesis testing, a review. The logical sequence for a researcher who wishes to engage in hypothesis testing is as follows. O. State the research hypothesis, e.g., there is a difference between the population mean of students using method A and the population mean of students using method B. O. State the null hypothesis, e.g., there is no difference between the population mean of students using method A and the population mean of students using method B, or the difference between the two population means is 0. O. Determine the sample statistics pertinent to the hypothesis, e.g., the mean of sample A and the mean of sample B. O. Determine the probability of obtaining the sample results, i.e., the difference between the mean of sample A and the mean of sample B, if the null hypothesis is true. O. If the probability is small, reject the null hypothesis, thus affirming the research hypothesis. O. If the probability is large, do not reject the null hypothesis, which means one cannot affirm the research hypothesis. 4. Practical versus statistical significance. A. One- and two-tailed tests. A one-tailed test of significance involves the use of probabilities based on one half of a sampling distribution because the research hypothesis is a directional hypothesis. A two-tailed test, on the other hand, involves the use of probabilities based on both sides of a sampling distribution because the research hypothesis is a non-directional hypothesis. B. Use of the null hypothesis, and evaluation. There appears to be much misunderstanding regarding the use of the null hypothesis. First, it often is stated in place of a research hypothesis. Second, there is nothing sacred about the customary 0.05 and 0.01 significance levels, they are merely conventions. Finally, there is also nothing sacrosanct about testing an obtained result against 0. V. Inference techniques. A. Parametric techniques for analyzing quantitative data. A parametric statistical test requires various kinds of assumptions about the nature of the population from which the samples involved in the research study were taken. Some of the commonly used parametric techniques for analyzing quantitative data include the t-test for means, ANOVA, ANCOVA, MANOVA, MANCOVA, and the t-test for R. B. Non-parametric techniques for analyzing quantitative data. A non-parametric statistical technique makes few, if any, assumptions about the nature of the population from which the samples in the study were taken. Some of the commonly used non-parametric techniques for analyzing quantitative data are the Mann-Whitney U-test, the Kruskal-Wallis one-way analysis of variance, the sign test, and the Friedman two-way analysis of variance. C. Parametric techniques for analyzing categorical data. The most common parametric technique for analyzing categorical data is the t-test for differences in proportions. D. Non-parametric techniques for analyzing categorical data. The chi-square test is the non-parametric technique most commonly used to analyze categorical data. The contingency coefficient is a descriptive statistic indicating the degree of relationship between two categorical variables. E. Summary of techniques. While the details of both mathematical rationale and calculation differ greatly among these techniques, the most important things to remember are as follows. The end product of all inference procedures is the same, a statement of probability relating the sample data to hypothesized population characteristics. All inference techniques assume random sampling. Without random sampling, the resulting probabilities are in error to an unknown degree. Inference techniques are intended to answer only one question: given the sample data, what are probable population characteristics? These techniques do not help decide whether the data show results that are meaningful or useful. They indicate only the extent to which they may be generalizable. F. Power of a statistical test. The power of a statistical test for a particular set of data is the likelihood of identifying a difference, when in fact it exists, between population parameters. Parametric tests are generally, but not always, more powerful than non-parametric tests.